think, oh, that poor individual.
Okay, we are in our last section of chapter 2, which means we'll be talking about instantaneous slope today. Oh, this is kind of bad timing. We'll review tomorrow and test on Tuesday.
I say we test on Wednesday.
Maybe we could like just have a food day tomorrow.
Yeah.
And then review on Tuesday.
Yeah.
I will consider.
Because testing on Tuesday is a bad idea. You know, big weekends, lots of time to forget. Just doesn't work out.
I will consider what I'm going to do.
And Mr. Sharp even said that. So, you know, I have sources.
He does know
Sharp said
everything.
it must be true.
Hey, don't go ruining my sources.
Okay, so our goal today is to find the instantaneous slopes of a function f of x and the equation of the tangent line that goes with that slope.
Oh boy.
So first we have to quickly talk about intermediate value theorem. We didn't have time yesterday. I wanted to give you a little time to work on the assignment. And it's something we need to see, and it works really well with continuity, which is why they put it with continuity. But the actual AP questions you would see using intermediate value theorem, we need a lot more information. So I'm not even going to ask you any questions on it right now. It's just so we get kind of a basis of it and a basic idea so that later on when we can actually questions involving can actually ask questions involving intermediate value theorem, we can refer back to something we've at least heard before once. So intermediate value theorem, it kind of feels like you're stating the obvious, but it actually has a purpose even though we're stating the obvious. So what it's saying is if your function is continuous between two x values a and b, then it would take on every y value between f of a and f of b. We'll draw a picture.
I was going to say, can you translate that into English, please?
Americans.
Yeah.
And this only works for continuous functions. And when you see the picture, like again, it will be like, oh, that's obvious. Even though the formal math definition is a little bit weird.
Weird, huh? It's because it's math and not English.
It's an entirely different language.
Yeah, they're so silly.
Okay, so here's my picture. We have a function. It is continuous. No holes, no jumps, no asymptotes, no oscillations.
That is a weird graph.
It is.
It's like
So all we're saying here is that this a, this x value a, goes with some y value. We have this point a comma f of a. So it goes with this y value that we hit over here. Then we have some b, x value again, that goes with a y value. And it's the parenthesis over there, but then I didn't want to squish it in. All it's saying is that if you selected x values in between a and b, we'd hit every y value between f of a and f of b. Maybe we hit it more than once, but we would at least hit every y value. Because the function is continuous, if I chose a random point in here, call it c, c must be between f of a and f of b. Wait, I said that backwards. C, we don't like the C analogy. C analogy does not work. Because I could pick C over here, and that's not between f of a and f of b. We're just saying somewhere between A and B, we have to take on all the values between f of A and f of B. We're going to hit every single one of these y values somewhere between these x values. So for example, let me give some.
So it's just on that graph, you'll go from all of it.
Yeah, we don't know if it hits any values higher than f of B or lower than f of A, but we know because it's continuous, we've got to hit the values in between. So here's a more concrete example. Let's say we have x cubed. You guys all know what the graph of x cubed looks like. And we consider the interval -1 to 1. Here's my x values. What are my associated y values with this? How do I find y values that go with x values? Plug it in. So my first y value, this is f of A, would be -1 cubed or -1. If I plug in f of B, I get +1. So right now, graphically, the information we know is that at -1 on the x-axis, I'm at -1 on the y-axis. At +1, I'm at +1. Let's pretend we don't know what x cubed looks like. All we know is the starting point and the ending point. But we do know x cubed is continuous. Am I going to pass through the x-axis if I draw any function between these 2 points?
That's continuous.
That's
Yes.
continuous. Yes. I have to. No matter what I draw, I could go like this. It had to pass through the x-axis to get there. Sometimes more than once. So that's all it's saying, is if we start one place and end in another, I have to hit everything in between. I could say, am I going to hit 1/2 at some point? Does our y value equal 1/2 at some point on this continuous graph?
I'm gonna say yes.
Let's look at our y value. 1/2 is about here.
I'm gonna say yes times 2.
3 times, possibly 4, depending on how accurate we are. Okay. Or I could have just gone straight from here to here, and then I only hit it once. But I'm required to go through 1/2. I'm going to hit 3/8. I'm going to hit, since we're only going from -1 to 1, I'm kind of limited, so I have to use a law of fractions. I'm going to hit 9/10. I'm going to hit -0.472. I have to hit every number in between these 2 values, somewhere, at some x value. I could hit more y values than just that. We hit like 10 up here. But if all we know is start and finish, we know we will hit the numbers in between. That's all intermediate value fairness says. Like I said, we're not going to have any questions on it right now. When they really use this for the AP test, it's within the context of a larger problem. So we can't ask the larger problem yet. We just don't have enough information. Okay, so let's find some instantaneous rates of change. We worked a lot with average rates of change. We found average rate of change in our warm-up today. So average rate of change, how have we been representing average rate of change?
F of B minus F of A over B minus A times fruit.
We could have said f of fruit or fruit of B minus fruit of A.
Fruit of bananas minus fruit of apples.
Something tells me we're hungry.
Okay, so now we need to focus on instantaneous rates of change. What did we say we had to do to get an instantaneous rate of change from this average rate of change? We talked about it a little bit.
Get very, very close.
Get it very, very close. So when we were using B minus A, this average rate of change, we had some graph. Say this is A, this is B, which means this is F of A, and this is F of B. We said, okay, if I take my average rate of change, it's like we're finding the slope of the secant line through these points. I want to get a better estimate. So if I want to get a better estimate close to A, I should pick a point closer to A. So I go here, and I find another secant line. And then I do it again. I pick something closer, and I find another secant line. So what's our ultimate goal? What do we want it to look like when we have the exact? Instead of a secant line, what should we do? We want a tangent line. And we're trying to get super, super, super close. Why couldn't we actually find the slope of the tangent line? What was our problem with that?
The world implodes.
What happens if I used A as both my points? What if I found F of A minus F of A over A minus A?
It's divided by 0.
It's divided by 0. But we wanted to get so close it didn't matter. How do we get really, really, really close to something? Lots of zeros and lots of 9s. What else have we learned calculus-wise that helps us get really, really close to something without having to hit it? It could, but it doesn't have to. Limits. We learned limits to get really, really close to stuff. So we want to find the limit of this average rate of change. I'm going to intentionally leave what we're approaching blank. So we want to be able to take this limit of the average rate of change, and that'll give us instantaneous rate of change. But here we run into another conundrum.
Did someone sneeze? If so, bless you.
B and A are two different x values right now. They're two different variables. So am I going to pick B approaching something? Or am I going to pick A approaching something? What would be the best way to do this? So we've got to change our notation up just a little bit so that we can incorporate the limit. We don't want two different variables. We want something that can be represented. It's still going to be represented by a letter, but we don't consider it a variable because it's not something. It's not changing in the way we use variables for. In calculus, we'll see a lot of constants that are represented by letters, but they're actually a constant. So let's look at this picture again. So I want to only incorporate one variable. Let's call this first one x. And somehow I need to involve x over here. But obviously they can't be the same, or else they would be right on top of each other. We're trying to find something that's apart. So we can actually label the distance between them as something. We're going to label it as h. because that's what they commonly use. So stick with their notation. So if this is x, and we have a distance between these two things, what would this one be? X plus h. If we had this was 3 and this was 5, 3 plus 2 would get us to 5. So if we just add that distance between the two, then we have some new notation where h is considered a constant because it's always just the distance between where we start to where we finish. So that means our y values now are f of x what would our top y value be? F of x plus h. You take the x value, plug it in. So now we need our average rate of change equation using this new notation. It's the same equation. It's still f of b minus f of a over b minus a, but we represent it as f of x plus h minus f of x over x plus h minus x. This is b. This is a. It's still the same equation. We're just representing it a little bit differently because now we can take our limit in a nice way. Let's simplify it first before we decide how we should take our limit. So the only thing we can simplify is down here. What's going to happen in the denominator? X's will cancel. X minus x goes away. So it's going to be h. So now we have f of x plus h minus f of x over h. And now we have to consider our limit. So if we want to take our point closer and closer, we want h to be smaller and smaller. We want h to keep getting smaller because we want the distance between where we start to where we finish to be small instead of big. So if I want h to get smaller and smaller, I want h to approach 0. So this is our formula currently for instantaneous rate of change. Don't forget we need to start bringing note cards. You got yours? Woohoo! This is something we would put on our note cards.
What's the notepads for? Just writing down formulas or something?
Yeah, they're for writing down formulas so you can use them to review instantaneous. Because there's so much to memorize that we need practice just memorizing stuff. So we're making our own note cards to just have a place to practice. So try to remember note cards. I'll probably do a note card check next Wednesday. That'll give you some time to get them, but then I can remind you on Tuesday in case you have forgotten.
Check. Is that like a quiz?
No.
Test?
That'll be worth points. That'll be worth participation points. Participation is 10% of your grade.
How much is homework?
15.
Oh, crap. Okay.
So, instantaneous rate of change. So like on the front side, I would want you to write instantaneous rate of change. Back side, exactly like that. Other note cards we should have done so far are average rate of change.
That's just
Where there was another one. I'll look them up since not everyone has
nope.
note cards yet. Then
Dang, you
I'll have a note card today.
Don't think you'll need that.
So let's use our new formula. We have a new formula. Let's see if we can use it. find the slope of the line tangent to the curve, f of x equals x squared, at t equals 1. So we know our formula is limit as, oh, I used x's and t's. They should be the same. So let's say at x equals 1. I don't know why I changed variables mid-example. So we have limit as h approaches 0. And we know our formula is f of x plus h minus f of x all over h. So of our variables, which ones do we know right now? We know x is 1. They told us specifically. X is 1. And sometimes they use a instead of x. It's basically the same formula. They just have a couple of different ways of writing it. So if x is 1, I can replace my x's with 1. So let's do that first. And since I have not done anything with the limit yet, I do have to keep writing it. It's a pain. Such is life. So now I need to do something else. We don't want these f of stuff. I want to actually use it. So we plug it in. That's what this notation is used for. It says plug stuff in. So 1 plus h, we're going to plug it into our function x squared. So we would have, limit still, not used it, so I have to keep writing it. For some reason it switched to lines instead of, there we go. Smartboard is possessed. Or an alien is controlling it.
Marche? Did you say Marche?
Mothership.
Oh, I was gonna say, I don't think Marche is possessed.
Okay, so we replaced everywhere I saw x for the first piece. These are two separate replacing problems. F of 1 plus h is just this replacing problem, 1 plus h squared. Over here, f of 1 is a second replacing problem, 1 squared. We just plug it in. We're just using that same function multiple times, and we're plugging in different things. So now, I can't solve this yet. I can't just plug in 0. It's a problem for us. So we learned some tactics. Now this is not a factor tactic because we can't factor right now. It's already factored. So what should we do instead? What do you think? Emma? Square it. We can multiply it up. So 1 plus h squared. Did you guys have Miss McDonald?
Once upon a time.
Long, long ago.
Don't make
She
us
should
sing
have
that
taught you a song.
Which
The
one?
first and last song.
The first and last one?
I sing that all year.
I can never remember the song. But if you remember that, that's
Wait,
one
is
way.
it first you square the first one, square the last one too, in between the first and last is first and last one too?
Yes.
I learned that from a senior friend of mine.
You guys didn't have
Trying to
Miss
actually-
McDonald? Okay. Or we can go old school and we can just write it out. 1 plus h times 1 plus h.
It is your destiny.
And we FOIL. 1 times 1 is 1 squared, or 1. 1 times h is 1h. And then we have a second 1 times h, so plus 2h. H times h is h squared. And then we still had to do our 1 squared here. So we have minus 1 all over h. And conveniently, the 1's go away.
It was very convenient for some reason.
And most of the time it works out conveniently
Almost
like that.
someone planned
Isaac Newton.
it.
Okay, so now I can factor. What can I factor out of the numerator now? H. So we have limit as h approaches 0 of h times 2 plus h. And also very conveniently for us,
Can't you
The,
split them off?
the ends cross out? Oh, right,
Just
the
go away.
H's cross out.
okay, be careful.
I'm sure that's neat.
This h cannot cross out with this h on the right.
That's because it's
Because
being
it's
added to
attached to the
something.
two. Yeah, it's being added to something.
It's
I
like
see that
splitting
all
up.
the time though, when you're so worried about all the
Really?
calculus stuff, you forget some of your algebra things.
Oh,
So now that I have no more h in the denominator, how do I solve this limit? Plug it in.
It's like super gross.
So this is the slope of the tangent line. Or, what's another way to say slope of tangent line? We also had instantaneous something, it's quite weird. Instantaneous velocity, usually we say instantaneous rate of change. Even though rate of change is just another word for velocity. Instantaneous rate of change. Or, we actually have the derivative at 1. We need to eventually find the derivative everywhere. We'll have derivative functions. But right now we have the derivative at 1, and that derivative is 2. But they all mean the same thing, but we need to know what situations to interpret what meanings for them. So we're going to take this same function, and now we're going to find the equation of the tangent line, whose slope we just found. So a tangent line is just a line. How do we find the equation of a regular line? What's the equation for a line?
Y equals mx plus b.
Y equals mx plus b, which
Trick question.
is the equation for a line, but it's not the most useful one for us right now. Yeah, we have slope, we have m, but we don't have a y-intercept, so that's a problem. What other equations for a line do we know? We know some different forms of an equation for line. I know, we have to think way, way back.
Standard form.
Standard form is ax plus by equals c. Also not helpful in our situation, but that is another form. There's one more I'm thinking of.
Y-intercept?
Close. Slope
Oh.
intercept. No, point slope form.
So like
Yes.
the Y1 minus Y2.
Okay. So usually we say y minus y1 equals m times x minus x1. This is actually something we will use a lot. And it can be helpful. So I often leave it in this form because it's the form we've seen most often. But most of the time we're actually trying to find the equation of the line, so we want y alone. So a lot of the time what they'll do is they'll write it with the y1 on the other side.
That's weird.
It does look weird because it's not the form we're used to seeing. And you don't have to do it that way. You can stick with the form we've seen and memorized for so long that it's easy for us to remember. But you could also consider it this way. And then you have one less step when you're solving for things. But we will use this formula a lot. It comes up in a lot of different applications.
Could I have today's
I gave out all my copies.
It's the
What's
blue
last
one,
two?
right?
Number 5.
Number 4?
Yes. And did you have a 3 with that too?
A what?
A 3 with that too?
How many do we need?
Yeah. Just hold on there.
Thank you.
Okay. So, right now we know the slope. What is the slope? Because we're using from example 1. We found the slope already. What is it?
2.
2. We also know something else. We know an x value.
Yeah, x equals 1.
X equals 1. They told us that in the first example. We have to use the x value that goes with the slope. So what's the only thing we're missing? A y value. So how do I find any y value at any time? Y values we find the same way every single time. Plug it in. So we plug x into our equation. What equation are we using? X squared. Since it comes from example 1, I'm writing it again. So if we plug in 1, we get 1. So now I can find the equation for my tangent line. Y minus 1 equals m, our slope was 2, times x minus 1. We can simplify. On the AP test, usually if they say find the equation, they want it to say y equals blah. So we would distribute 2, and we would add 1 to both sides. So the equation of our tangent line is y equals 2x minus 1. So let's check. Let's draw our graph and see if this looks like the tangent line.
Are you recording this?
Yes.
Oh.
But the only people who are likely to watch it are you guys.
I'm gonna post it on Facebook so everyone can listen.
Everyone wants to watch a 50-minute calculus lecture just for the random comments about mothership.
It would be so
I
fun.
totally would. There's someone found this.
I have all kind of friends who
I
brought
have
it.
a few friends that are like, ooh, calculus lecture, let's watch that.
And they'd be like,
They're ruining my calculus experiences.
Sorry, I forgot to load TI Inspire again before we
it's okay.
started.
I was about to read what it was saying and then Josh reminded me.
Okay, so we need to go to our graph screen. We want to just graph both on the same set of axes and see if it looks like our tangent line. So we do x squared. How do I get back to graph a second thing? Tab. And the equation of our tangent line was
2x minus 1.
2x minus 1.
Oh my gosh.
Okay.
Whoa.
Does that look like?
It's a red and blue wine.
Yeah, since they're colored, they'll draw the different graphs in different.
I like how they do that.
You could make them the same color. You can pick your color.
State versus the UV, which is happening tonight at 6 o'clock.
You can?
Yeah, if you go tab and let's go to this. You should, I think you can. I know you can pick a lot of different things about it. We'll left. It does. Line weight. Like I know for sure you can change it to dashed and stuff, but does it not let you go over to color and change?
No, I won't let us.
Oh, that's sad. Okay.
You just have to scroll down to like 6 and it'll be.
I thought you could. Practice continuous, label style. Nope. Maybe there's a way, but I don't know it. Okay, so now we've found the tangent line at that point. That's been our entire goal so far, is go from secant lines to tangent lines. Okay. So, let's try something a little trickier. Where would the slope of f of x equals x squared equal 1/8? this is a little bit trickier. Because we know where the slope equals 2, but that's specifically at x equals 1. We're trying to find some x value now where the slope would equal 8, or 1/8. Well, when we're looking at the graph, so you're saying, like if I drew a tangent line here, would that slope look like 1/8, that tangent line? That looks like a pretty steep slope. If we're going to have a pretty flat slope, where should I put my point?
More towards the
More towards this. It's somewhere over here. So now we have a general idea of where it would be, but we still need to be able to find it exactly. So, I know slope should equal 1/8. What is our formula to find slope?
Y equals m.
That's the equation of a tangent
y
line.
minus y2 over x.
That's slope algebraically. How do we find slope calculus E?
Cry.
We just learned a formula to find slope, but we called it something else.
Instantaneous one.
Instantaneous rate of change. That is another word for slope. H, not X. This whole thing, it's slope. Fancy calculus E slope. But the y2 minus y1 over x2 minus x1 only works for straight lines. This is slope for anything now, for any curve. So what do we want the slope to equal? 1/8. It told us where would the slope equal 1/8. So we want to know where does this equal 1/8. So we've got to do some pretty heavy algebra at this point. I'm going to need more room, so I'm going to extend the page really quick and drag stuff down so that I don't have to do it in the middle of the process, hopefully. So, what did we start with before? Before we knew what x equaled, and we plug in x equals 1. But now we don't know what x equals. So what was our second step? If we don't know what x equals, what did we do after we plugged in 1? That, I think you're thinking of the equation of the tangent line. We're looking at example 1. On example 1, we plugged in 1 for x, and then we did a second step.
And then
That was actually the third step.
that's a third step.
That was
Got rid of
the third
the
step.
F.
We got rid of the f. We did something to get rid of f. How do I get rid of f?
You plug in.
Plug it in. Since our function is x squared, we square it. I could have used a different function, but x squared is kind of nice to work with in this form, so I kept it to an easier one. So we have x plus h squared minus x squared. If I plug x into x squared, I still have x squared over h. So now, a bunch of you have skipped to this step. What do we do next?
Multiply it out.
Multiply it out. X plus h squared. If I write it to the side, x times x is x squared. X times h is x, or hx. Then we do inner. H times x is hx again. Then we do last times last. H squared. I know, it's a lot of variables. So, this can combine to be 2hx. And now we can go over here and plug it all in. We have limit as h approaches 0, x plus h squared is x squared plus 2hx plus x squared. That was our
You
side
wrote
work.
X squared twice. So there should be an H squared.
Thank you. Minus x squared all over h. So conveniently, what happens?
The X is crossed out.
X squareds cancel out. And what can I factor out of the top? H. So we have h times 2x plus h over h. I could plug in 0 for h. Now I can take my limit. No, I just needed 2x plus 0. I don't do it. So now we found a slope function. I could find the slope anywhere I want. What would happen? We already found slope somewhere. Where did we find slope in example 1? At x equals 1. 2 was the answer. So if I plug in 1, do I get the correct answer?
Yes.
We get a slope of 2. So if I have this slope function, I can find the slope for any point I want much more quickly. I can find the slope at 200. What's the slope at 200?
400.
400. Plug it in. What's the slope at negative 50? Negative 100. So it's a slope function now instead of just slope at one point. And that'll lead us more into derivatives in next chapter. But we wanted our slope to equal how much?
1/8.
1/8. So we want to know, where does 2x equal 1/8? Now we just solve an algebraic equation. How do I solve this?
X equals 1/16.
X equals 1/16. If we divide both sides by 2, that is the x value where our slope is 1/8. I think we're not going to have time for homework today. We've got to get through this last little part. It's not enough to move it into an entire new day. So let's talk about normal lines pretty quick. The example is pretty quick since we already know the slope. A normal line is perpendicular to a tangent line. What do we know about perpendicular slopes? Again, we have to think all the way back to algebra. What do we know about perpendicular slopes of lines? They do cross. They're opposite. We need a second word. Reciprocals. Okay. So if my slope is m, the slope of, so if my slope of the tangent line is m, the slope of the normal line would be negative 1 over m. Flip it, change the sign. So what if I want to find the equation for the normal line now? I still am finding an equation of a line, so I still use y minus y1 equals m times x minus x1. But now my slope is going to change. What should my slope be? What was our slope for the tangent line at 1? 2. So what's the slope of my normal line at 1? Negative 1/2. So slope is negative 1/2. We already found x and y earlier. We don't need to find them again. Found them once when I was finding the equation of a tangent line. And they told us what x was. I really only had to find y. Now a common mistake is to take the equation for a tangent line and just flip the slope there. But if you've already simplified, then you don't take into account that that slope changing changes some of your distribution stuff. So we kind of have to just plug it all in one more time. Y minus 1 equals m times x minus 1. So we simplify again, we distribute. Negative 1/2 times x is negative 1/2 x. Negative 1/2 times negative 1 is positive 1/2. And then we add 1 to both sides. So what's 1/2 plus 1?
3/2.
3/2. So again, let's check if they're perpendicular. We can see what that looks like on our graph. Let's go plot this line. 1/2 x, oh wait, what did I write wrong? Negative. It's an easy way to lose points because it's easy to drop those little, you have to be so detailed. So we go to tab again. Now mine has a whole bunch of lines I drew in. Negative 0.5 or negative 1/2, either way you want to write it. X plus 3/2? Yes. Anthony?
Is this your calculus class?
Yeah.
This is so much smaller than ours.
They're very quiet too, unlike.
Oh my gosh, I know, I'm sorry. But I don't even have a math class this year.
Huh?
So.
Hey?
Doesn't matter.
See ya.
That's the class you watch.
Yeah, he was one of the juniors from last year. They were very noisy.
How many people are in that class?
20. Started like at 30 and it ended at about 20.
20. So like almost 3 times what's in this class.
Hopefully you'll all stick around. Just ask. Don't leave. Okay, so does our line look perpendicular? Yeah, this looks to be about a right angle. So now we know we did find the normal line. Okay, so we just have one last example. Let's not even write it down. I just wanted to put this in terms of a word problem. So just so we can think about what happens with word problems. So Evelyn decided, she was sick of calculus, so she threw her pencil at me.
Let's go for it.
In disgust. Not just threw her pencil, threw it in disgust.
I say we watch
So.
an example. And then people show me.
Oh, dang.
I'll let you borrow one, yeah. We have a couple over here.
Her pen at Miss Barton in disgust.
I see what you did there.
Oh,
If
wow.
the pen follows the position function, negative t 16t squared plus 14t plus 3, which I will have you know is an actual, if you've done any physics, which I think some of you have, the actual throwing an object function. And it hits Mrs. Barton at 0.5 seconds. So what velocity is the pencil traveling when it finally hits Mrs. Barton?
So it turned from a pen to a pencil.
It's a magic pencil.
That was
Or pen.
impressive.
It just does whatever it feels.
It is. It's both.
He's back.
Yeah, I already know the answer.
You should join our class.
Yeah, but you know
Stop
the
being
quick
smart.
way. We don't know the quick way yet.
I'm just like, okay, we're done.
Give me the answer quick.
So, if it asks you to find velocity, we still know how to do this. They just asked it a different way. What is it asking us to find? Instantaneous rate of change. It's another way to say, let's find the instantaneous rate of change. So if I'm
Slope.
finding, which is slope, okay? Instantaneous rate of change
Bless you.
is slope. So if I'm finding, I would just do our limit as h approaches 0, f of what's our x value that we're trying to consider? Or t value, sorry. Working in t.
Oh, I understand.
0.5 plus h minus f of 0.5 all over h. And we'd go through, plug it in, simplify. We don't have to go through the whole problem since
It's
we're
negative
running
2.
out of time. It is.
Yes.
That was quick.
Yeah, I know.
Josh
I'm
is
just
a genius. Amazing. So we would do the same thing. It's just a different way to present the same type of problem. It's telling us to do the exact same thing.
Once you guys get to derivatives, you guys are gonna hate limits. That's all I'm gonna say.
I know.
We were all pissed off when you told us that. You're like, now there's an easier way. We went, are you serious? What is this?
You gotta know where the easier way came
Oh,
from.
so what you're
Hey, well,
telling
we
us
got
is
both. I got a 3 on my test, so it's okay.
Good job.
I got a 4 on my AB sub-score though.
Awesome.
So I feel good about it.
You could retake it this year. Get a 5.
Keyword is could. Do I not have to take the class? Can I just come up, just show up? All right, let's take this again.
You could.
I don't see why I couldn't.
You could be my calculator.
Yeah.
I'm not
You
an
can help
Asian,
me
I'm
with my
sorry.
homework.
Take
You
the
just
eyes,
have to
man.
pay,
Take the
you
eyes.
know, another $80 to do that. Or I guess it's almost $90 now.
Sure.
Yeah.
I'll just take AP English.
Yeah, well,
Screw myself.
A couple of years ago, it was only like $80, and now it's like $85.
Last year was.
It does keep-
With tax.
Are you kidding me?
It does keep going up.
I paid $90 and put it
They're like, oh, you want college credit? Let's just keep pumping it up.
And college credit
Because
alone
it's-
costs.
Because it's a lot cheaper
Yeah.
to do the AP test than it is to just get college.
Unless course your college you're trying to go to doesn't make sense.
So we don't have time for homework today. There's no
Oh,
time
good.
to book us out. We
So
don't
we
have
can-
time to start in class.
Dang it.
You
No,
almost
we don't
made me
have
happy
time.
inside.
We twisted your words quite frequently last year too.
Yeah, every student does, every year.
Yeah,
What
it's-
students do.
It's expected though, isn't
So
it?
were you one of those students that always did their homework on time and always turned everything in and was just like the perfect, were you
No.
the-
No.
the-
No, I can attest to that.
Or are you like Ben, who doesn't even know what a homework assignment is?
That's
I know.
not true.
I know what it is, I just,
Start of the year, I was quite a bit more diligent. End of the year, some of it was like, well, I have work. I don't feel
Oh, I
like
thought I
doing
stopped
it.
recording.
Oh, I don't know what to do
Stop.
anymore.